Our third question is leading into what are the mechanisms involved in heat acclimation, and we're just going to be describing and what they do. So we actually have three primary mechanisms. We have our hormonal regulation, osmotic gradient, and then our cellular adaptation. I'm going to wait to kind of draw it, and then at the very end I'll pull it back together. So our hormonal regulation, our sweating is going to reduce our plasma volume, activating, bear with me on this one, renin, angiotensin, aldosterone system, or our RAS system, or I guess RAS. Aldosterone increases our sodium reabsorption in the kidneys, and this promotes water retention. Concurrently, an antidiuretic hormone, or ADH, increases our water reabsorption in the renal collecting ducts. So together these hormones restore and expand our plasma volume after sweating. The osmotic gradient, so sweat is a hypotonic relative to plasma, which just means it's less dense. As a hypotonic fluid is lost, plasma osmolality rises, and this stimulates thirst and fluid retention to restore osmotic balance. So over repeated exposure, our sweat glands are going to actually improve sodium reabsorption capacity, and it's kind of a little bit mediated in part by aldosterone. And lastly, we have our cellular adaptation. So repeated heat exposure increases total body water and may expand our intracellular volume. At the molecular level, heat stress induces heat shock proteins, which is that SP70, HSP70, HSP72, HSP90, and HSP70 and 72 actually function as molecular chaperones, basically. So they're just going to stabilize our protein conformation, which will prevent our denaturing. And it's actually going to inhibit the proteins that actually inflame our muscles, such as like NFKB, TNF alpha, IL-6, and HSP90 contributes to protein folding and cell survival. HIF1 alpha actually may also be activated, which influences gene transcription under stress. So these molecular responses actually enhance our thermal tolerance, our cellular integrity, our immune signaling, and potentially even our insulin sensitivity. Over time, heat stress may also stimulate pathways such as like mTOR and IGF-1 signaling, which links thermal stress to muscle remodeling and recovery. So how we're going to tie it back, so like if we look at our hormonal mechanisms, we're going to see if we sweat and we have some loss in there, it's going to decrease our plasma volume. It's going to activate RAS, which is going to increase our aldosterone, which is going to increase our sodium water retention, or sodium and our water retention. And then it's going to expand our plasma some more. And then we're also going to have an increase in our osmolality and an increase in our ADH, which is our antidiuretic hormone. And then that's where we're going to get our water retention as well. If we have our cellular side, so we're just going to do this. I'm just going to write cell. Then we're going to have some heat stress from that high temp, which is going to increase our heat stress proteins, so HSPs. And then that's going to promote protein stability, reduce inflammation, increase our cell survival, and increase our thermal tolerance. Okay, bye.